Swayam Prabha. Digital India. Educated India.
With second part of the lecture, emerging perspectives in quantum optical spectroscopy. Again, as noted earlier, there are more questions than answers in this context, so bear with me, and I'm hoping to inspire some of you or all of you to kind of explore this direction. This is really a field where a lot can be done. You can call it blue space, that's what they call it, right? Blue space, blue sky. Blue sky, there's nothing done there, so there's a lot of scope. But it's also challenging because there is nothing done, and one of the challenges has been, okay, where should we begin with? And that's why it's kind of exciting as well. Okay. So SPDC photons, I already mentioned when I have spontaneous parametric down conversion process, where I have a pump, a blue photon down converting into a green and red photon. For example, high energy photon converting to two low energy photons, intrinsically is quantum entangled. For the sake of completeness, I want to define what quantum entanglement means, and for that you need to first understand quantum superposition. We all know what quantum superposition is. I could take two states and create a superposition state, a coherent state. I kind of think about it like a spinning coin. Spinning coin is in a superposition state. It's kind of a nice analog. I could think of this superposition, for example, in the context of a photon. It could be 0 and 1 states, could be, for example, the polarization of the photon, electron spin of the photon. But these 0 and 1 state can also be something else. It could be the frequency of the photons. It could be spatial degrees of freedom of the photon, so on and so forth. So is a superposition state, but let's say I have two photons now. They're both spinning, are kind of in a special case of quantum mechanical superposition, which we call as entanglement. And we say if the measurement of one system is correlated with the state of the other system in a way that is stronger than the correlations in the classical world, then we say they are entangled. In other sense, the two systems are not separable. They cannot be separated out and described independent of each other, and they're also indistinguishable. Okay, these are the two important properties of quantum entanglement. I'm sure all of you know what quantum entanglement is, and you have explored in detail. This is a kind of a very basic level kind of description of quantum entanglement. The way I think about it is that if I have heads and tails of two coins, I spin them both. In classical world, if I stop one, the other will continue to run, and if I get head, it's not let's say expected that other will be also head or tail, right? We cannot, they're too independent. If they're entangled, then if I project one of the coin on head, the other gets projected onto, for example, tails, and if I see tails on one, then the other one becomes head, for example. Then there is entanglement between this, and this, as you can already kind of see from the analogy of the coins, it's not something that you can be perceived. This can be perceived in a classical world. It's only a consequence of quantum mechanics. So one of the first experiments, in fact, which kind of explored the indistinguishability aspect of entangled photons specifically, is Hongo-Mandel interferometry. So in Hongo-Mandel, coincidentally, which was also done, I think in the Hongo-Mandel paper was published also in 1986. Seems to be 86 to 89 to 90. Those 4 years were pretty momentous years. A lot of very foundational quantum optics was done in that period, which is kind of very fascinating to think about. All right, in Hongo-Mandel experiment, what do? You come with your pump. This is your crystal. You generate your signal on idler photons. let's say your signal photon, you send it on a delay, you add a phase using a delay stage here, like any interferometer, then bring them both back onto a beam splitter, the interferon beam splitter, then you detect using two detectors. Now, the thing that we will do in Hongo Mandal is a detection mechanism where you don't just measure numbers on both detectors and take difference or sum like you did in the last case, but we do a special detection called coincidence detection. Coincidence detection is basically when you're basically counting the number of times where both the detectors detect a photon at a given time, at the same time. So there's a certain time window. So you could have photons, for example, detected on one where there is no click on the other, or vice versa, and these are uncorrelated photons. You're not detecting. Coincidences are when both the detectors turn on at the same time. Coincidence event. Okay. So at the beam splitter, what happens? At the beam splitter, if the photons are indistinguishable, I should be able to write all possible interference pathways, right? I can have this condition where my two photons come in and they're both transmitted. I can get two photons. This goes this way, this goes this way. Yeah. So this is a beam splitter. So this photons come here, this photon goes this way, this photon goes the other way, or this photon goes this way and gets reflected this way, or this photons come this way and reflected the other way. And because one is transmission, other is reflection, there will be some kind of phase kind of scrambling or phase delay between the two terms. So basically these two terms cancel each other. And you could also have condition where one is reflected, other is transmitted in one direction, or the other is reflected and transmitted in the other direction. Now, of all these four terms, you will see that these two will not give coincidences, because in this case, you detect both the photons in one detector or the other detector, where two detectors will not turn on simultaneously. So this will not give coincidence, and you'll only get coincidence here. Okay. When they're indistinguishable, meaning that the phase delay between them is exactly zero, where you cannot distinguish between them, you will see that there will be a destructive interference between these two coincident terms because of the phase lag between the transmitted and reflected fields. And so you will see this characteristic dip in coincidences as you scan the delay. So go back. So you're delaying this, right at the phase delay to be zero, you will see a coincident dip. Of course, if you increase this coincident delay, these two no longer will be equivalent, and then you will not see a complete loss in the coincidence. Okay, this is a characteristic Hongo Mandal dip. It was published in 1987. Okay, fair enough. Something to note is, look at the number of coincidences here taken in 10 minutes. Okay, this is the first experiment. They do the measurement for 10 minutes. When there's not a measurement for 10 minutes, they were measuring coincidences rates integrating over 10 minutes, and they were getting barely 800 coincidences. And we can say that we are in a much better shape. Probably we should be getting at least 800 coincidences per second, if not per 10 milliseconds. Right? That's the rates we want. The modern sources are working with. So it was an extremely challenging experiment. It's not an easy experiment. Even today, it's not an easy experiment. It was not easy in 1987. Something that we should appreciate and acknowledge. Okay, so this is the seminal Hongo Mandal interferometer, and this is kind of to-go kind of method to establish the indistinguishability of my SPDC photons. Okay, fair enough? Good. Now it so happens in 2017 this paper came out. They did something very simple. So they introduced on one of the photons, let's say I have one photon which is not getting delayed, they added a sample which is resonant with the frequency of my photon, which absorbs and transmits a bit. It's not fully absorbing. Now without the sample, they saw a nice Hongo Mandal dip. There are some fringes here, and these fringes can be explained because of some finite bandwidth of my SPDC photons. And what they saw is that they saw that in the presence of the sample, the Hongu-Mandel dip substantially got modified. The interferogram got substantially modified. Okay, you see a beautiful kind of defacing like oscillations that kind of last for about hundreds of femtoseconds, okay, which is kind of fascinating. And in this particular paper by Kalashnikov in 2017, don't think of AK-47s, okay, but this is Kalashnikov, modern Kalashnikov. They were able to kind of explain this by saying there is some kind of convolution of my SPDC 2-photon amplitude with the homogeneous line shape of the sample. We all remember homogeneous line width. So somehow, for some reason, there is some kind of impartation, kind of manifestation of the defacing rate of your coherence onto Hongu-Mandel interferogram, which was kind of fascinating. The explanation was still rudimentary, so we tried to do a bit more advanced model where we considered some linear response function, yes, and when we write down the expand out considering a Bell state, a maximally entangled state, frequency entangled, and write out the expression for my Hongu-Mandel interferogram, we kind of see that the response function or the system response nicely gets into the response function, right? So the sample basically introduces sort of additional phase lag on one of the photons, which can be formally introduced as some form of scattering response function, linear scattering response function, which has coincidentally only contribution from homogeneous line width. We have done this. If you are interested, there is more details in this quantum science tech paper published a few years back right now, where we not only considered some sample response, but also we put strongly coupled microcavities. Now, luckily for this, because it's all done quantum optics based, we don't need to worry about weak interaction limit and so on and so forth. We can put strong light matter coupling, so we treat polaritons as quantum particles. So in quantum mechanical, we can treat polaritons. And what we saw is that as you increase the light matter coupling, there has been a dramatic change in the Hongu-Mandel interferogram. Okay, and this is basically capturing the linear response of polaritons even beyond defacing. In a weak coupling limit, you have defacing, but there is something going beyond as well in defacing. Now, this looks fascinating, right? This looks fascinating because, first of all, this is a CW experiment. CW because you're not using any ultra-fast lasers here. We are using CW light. Generating photons, you're doing at extremely low light levels, and you get access to sub-100 femtosecond dynamics. Right? Spectacular. That's one important thing. But more importantly, we have discussed extensively how to measure homogeneous line width in material systems, and we have already highlighted how homogeneous line width, the fluence dependence that we kind of spoke about, that we extract from 2D line shape, has a problem that we cannot directly measure the homogeneous line width at zero or close to zero excitation density, right? Without any bath. That's what we wanted to measure, and we had this discrepancy. Now, it will be fascinating if we can use this Hongu-Mandel method where you're literally sending a single photon at a given time, and if you can access the system bath interaction parameter, homogeneous line width, through that, it would open up completely new perspectives on accessing many body interaction parameters. There's only one photon going through. It's a linear response, but basically you are capturing the coherence response function using interferometry at single photon level. Okay. Now, the question is, can we really measure the intrinsic defacing rate with quantum light? The answer is, we still don't know. If anybody is interested, my lab is actively pursuing this. We still don't have an answer. The reason is the Hong-Mandel interferometer is non-trivial, especially when you have to think about putting a sample in between. It's even more complicated, but this is something that we are actively looking. There has been one or two other reports after the Kalashnikov report trying to reproduce this, and it is reproducible but still challenging. Okay, so that's a very interesting direction to pursue. Okay, questions? Okay, so in Hong-Mandel, we are strictly not measuring the entanglement. We are measuring the indistinguishability between the two photon states, which are part of an entanglement state. It's not really a measurement of entanglement. So now we can kind of go back and say, hey, can I really use something of entanglement to not only do a measurement, which is beyond short noise limit, or accessing a very important linear response parameter, but capture something which my classical spectroscopies cannot even comprehend, cannot even enable us to access, right? So in that sense, if I think of photon entanglement, okay, this is basically the generic representation of an entangled state generated by SPDC. You have two creation operators acting on a vacuum state, right? This could be a Sigler and Idler creation operator acting on a vacuum state. It will generate your SPDC state, right? Your quantum entangled state. Now, there can be many degrees of freedom associated with these two states. They can be polarization entangled, which means you can kind of not know what exactly is the polarization unless you measure one, then you know the other, right? They can have temporal / spectral. So it kind of correlated in one sense. You can kind of say, I don't know which color my photon is, or unless I measure one, I will know the other. Right? I can also have spatial degrees of entanglement. So you have different forms of entanglement that is available to you already in the quantum optics community. They are actively pursuing all of this. Now for spectroscopy, what is the most important thing? So a very important thing that we need to ask ourselves, this is something that I have been asking and thinking about for quite some time, is when I think of photon entanglement as material probe, three important questions come in. What kind of entanglement should I use? Okay. What is the actual measurement that will give me something? And third most important thing, what is the material problem to address? Okay, that's three important parameters, three important questions that one has to always think about. Right? Especially in the context of this emerging techniques, I want to kind of leave you with these three questions to think about also when in your own pursuit in the future. If I want to use really photon entanglement, we have to understand this. Otherwise, if I have to do a complicated measurement to access things which I already can get with a classical, let's say, linear absorption spectroscopy, it is not worth it. So this is very important kind of thing. So I'm going to start with something, a kind of a suggestion. I can use polarization entanglement, right? And I want to do the measurement. I want to characterize the whole polarization entanglement. And there is a process, there is a method called quantum process tomography to do that. With which, what is the problem to address? I will show you an example possibly, but it's still kind of underworked. We need to still think about it. So I can generate polarization entangled states, something of this kind. So this is generated in twinned BIBO crystals. You come with 45-degree polarization. This is type 1 crystal. You generate along one singular cone. You won't see two cones in perfect thing. You'll see a singular cone, and along the cone, both your photons will be either both horizontally polarized or both vertically polarized. Okay. So how do I characterize this? What kind of setup I need to do? I will do what is called quantum process tomography. So you come with a laser, you generate two light, and then you separate the two photons out, and you send them each of the photons through two polarimeters. How many of you know about polarimetry, where you take light of whose polarization you don't know, you want to characterize it? How would you do it? Anybody? Nothing quantum about it, classical. There is a light source in your lab, right? A new laser or something that you have bought, and you don't know what polarization it is. What would you do? Polarizer. Okay, Sudarshan, very good. So basically, you need to evaluate what is called Stokes parameters. Stokes parameters will basically characterize how much of your light is linearly polarized, or first of all, how much of your light is unpolarized, how much is linearly polarized, diagonally polarized, and right or left circularly polarized. So to do that, you need to do a series of operations with a linear polarizer, which enables you to project your photon on to a basis defined or the points of either horizontal or vertical. Then you need a half wave plate to project on the diagonal anti-diagonal axis, and a quarter wave plate to project on the right or left circularly polarized. And then you measure intensities, right? You do this 4 measurements. Basically, you take, of course, half the intensity irrespective of polarization. You measure only horizontally polarized light and see how much is that intensity. You take light polarized at 45 degrees, and then you take light polarized, for example, along right circular polarization. To do each of that, of course, here you don't need anything. Here you need a polarizer. Here you need a half wave plate. Here you need a quarter wave plate. You need to put all of this to do this measurement. Okay. Typically, you will get intensities. When you do in quantum domain, you're actually measuring numbers, because you're actually doing measuring some kind of expectation values associated with your density matrix. Remember, at the end, if I want to really characterize my quantum state, I need to be able to estimate the density matrix directly. So this is single qubit tomography, and these are your Stokes parameters. Okay, Stokes parameters which associated with N0, N1, N2, and N3, which are basically numbers that you measure with your photon detector, numbers with photon detector, doing each of this operation. Clear? Everybody is clear? Now this is for single qubit. We have 2 photons. Obviously, we have to do it on the 2 photons, right? When you do it on 2 photons, by the way, before doing that, now how will I get density matrix? Basically, you take all these 4 parameters, then expand and create or construct your density matrix using polyspin matrices. Very nice way of doing it. So your density matrix is a sum of these polyspin matrices multiplied by Stokes parameters. Okay, and then you can construct a density matrix of a single qubit. Fair enough? In the polarization basis, of course. Okay, so I have to do this for 2 photons now. So I have to repeat this. So in this case, my density matrix for a multi-qubit case will be a tensor product of my poly matrices, right, with associated extended Stokes parameters. And of course, the number of measurements for a single qubit, it's 4. For 2 qubits, it will be 16, and so on and so forth. It will increase dramatically, right? Because you need to project each of the photons on different bases and then do a measurement. So the way to do this for a measurement is you're basically doing this measurement at the end of the day. You take each of the modes and you project them either on horizontal, vertical, right circularly polarized, or diagonal polarized. Okay, you do a set of 16 measurements. Okay, at the end, the number that you are measuring, remember we are measuring entanglement here, it's not number, it's coincidence counts. So you need to measure the coincidence counts, and with that you can develop your density matrix. Okay, fair enough? I mean, I want to show this, but it's not an ideal thing because it is not a maximally entangled state. So let me skip now and show actual maximal entangled state. This is again 2018, a seminal paper came out, one of the only papers where they use quantum process tomography as a material probe. Here what they do is exactly like Hongu-Mandel. Okay, now they use polarization degrees of freedom. They do a polarization degrees of freedom, and without the sample, they measure the density matrix. This is basically a density matrix associated with the maximally entangled state, with one photon horizontally polarized and one vertically polarized or otherwise. Okay, and that's how density matrix looks like. The real part exists, the imaginary part is 0. It's kind of fingerprint of a maximally entangled state. Now what they do here, if you look closely in this, they put a microcavity here, strongly coupled microcavity, polariton microcavity. Okay, they put this microcavity, they repeat this measurement and calculate the density matrix. Okay, nothing much changes. Everything is remaining. Linear response is remaining the same. Now what they do is something fascinating. They come and photo excite this microcavity. So create a background of polaritons. They create a background of polaritons. Now the density matrix after certain density starts to evolve, start to change. So that is captured by this parameter called concurrence. It's another word in quantum information science. It's related to the purity, not purity, the quality of entanglement, which can be extracted from this density matrix. I'm not going to the math of that, but you see the concurrence does not change for a lot of range in the power, and dramatically at higher powers you see a dramatic change. Okay. Strangely enough, this is not super well explained. This is what they call a single photon nonlinearity. So the idea is they send single photon inside and that experience some kind of nonlinear behavior and starts mixing with the polariton state, thereby dropping the purity of the entanglement state. Okay, so there seems to be some kind of scope here where if I characterize the density matrix of my photon entirely, in this case, if you think about system bath interactions, my photon is no longer a perturbation in my system. My photon is a system. I'm characterizing my system completely and rigorously. I'm capturing the density matrix of my system. My bath now becomes whatever is in my material. Okay, in this case, a density of polaritons. Okay, I'm tracing of my system. At some point, my system bath interaction is so strong that my system is no longer pure. It starts to be a strongly mixed state and gives you access to some system bath interaction parameter, which is what we are interested in. Right? Now, what exactly does it give? What kind of interesting parameter does it give? Again, it's an open question. The theory is underdeveloped to kind of, not underdeveloped, it's kind of also challenging to kind of pinpoint this. It's another, let's say, fertile ground to explore. Really fertile ground to explore. Okay, so we spoke about Hongo-Mandel interference, where we started looking at indistinguishability. Then we spoke about polarization entanglement and characterizing the full density matrix in the presence of a sample. In both cases, I have only one photon going through. Okay, I will show you one more. So this is our perspective. Now let's say instead of sending one photon, I will send both the photons to the sample. Now you'll say, come on man, we don't even understand one photon what happens. You're sending two photons. I agree, hold that thought, but that's a perspective that we are developing. And if you're interested, these are a bunch of theory papers. There's actually one more now and two experimental papers at least, and we are hoping that one more will come soon. But this is what we are developing in our group. Tomorrow's talk, I will go a bit more into detail on what all this is. But at the heart of this is we define spectral entanglement as our degree of freedom, because we are doing spectroscopy. If you are doing spectroscopy, energies of the photon is the important observable for us. So we track this. Now I'll talk about how this looks like, but it's characterized by this F function here. This is what is called joint spectral amplitude. In our perspective, any kind of material interaction will transform this joint spectral amplitude. Okay, and our goal is to do a quantum measurement, which is basically characterizing the amplitude and phase of this joint spectral amplitude. That's our perspective. Again, it's an emerging perspective. I'll show you, define first what joint spectral amplitude look like and how we can actually do this measurement. We figured out a way to measure this. We are still developing a method to measure this. And later on, I'll show some theory to show that this is indeed possibly an important measurement which can give access to many body interaction. Tomorrow's talk, I'll show an actual experimental measurement. Okay, so SPDC. So if I write out the Hamiltonian for SPDC process and go through the math of this, this can be shown. It's about a couple of pages. It's not impossible, at least for the collinear degenerate case. But you can show that the wave function of my entangled state can be written like this, where I have my signaler and idlers creation operators operating at omega at two different frequencies, for example, acts on my vacuum state. Remember, this is an integral over all y possible frequencies. the most important parameter is this parameter here. This is what is called joint spectral amplitude, or JSA, which characterizes spectral correlations inherently present in my SPDC state. Which means if I detect my signal, by the way, this is idler, I don't know why it lost, this is idler wavelength. If I detect my signal to be 690 nanometers, then my idler has to be whatever 680 nanometers, so on and so forth. This, by the way, are simulations of joint spectral amplitude for type 1 and type 2 phase match BBO crystals, actually, with a pump at 343 nanometers. Okay, so everybody is happy with this spectral correlation function, right? So how do you do this measurement? What kind of measurement it will be? The simple way to do it is, okay, I come with two photons. Let's say somehow I separate them. Maybe I'm using some polarization trick or whatever. I can separate them. I send them through spectrometers, grading spectrometers, put a detector, and do a coincidence measurement. Now what I do is I change the grading at different wavelengths concurrently and build a 2D map. If you want to do this, good luck with it. Because it will take you forever to do this. Remember, you're working with SPDC photons with extremely low photon count rate. Then you're sending through a grading spectrometer, which is lossy. And then you're taking one order of the grading spectrometer, which means more than half the photons are gone. And then you have to do this slow scanning of two gratings, which will take forever. So because of that, we came up with a slightly different scheme here. If you're interested, read this paper. This was actually pioneered by the Cerullo group. We kind of used it for our SPDC photons. Basic how it works is a kind of a Mach-Zehnder interferometer, inline Mach-Zehnder interferometer, which uses polarization tricks to kind of do interferometry. What we do is we do interferometry, we Fourier transform this, and we get a spectrum. Okay, and then we can write this giant spectral amplitude in time domain to be like this, and then we can do a inverse Fourier transform to access the giant spectral amplitude. Technically, we are accessing giant spectral intensity, not giant spectral amplitude, because we're not characterizing the phase. Some examples here. Tomorrow again, I'm going to talk more about this. This is an experimental spectrum. This is a simulation. We can even do better than this. This is a real interferogram that's taken. You take a Fourier transform, it looks like this. It's kind of beautiful to look at. Okay, so we can measure joint spectral amplitude. By the way, this should not take more than a few hours. It's reliable and very stable system. It's inline interferometry, so it's kind of very stable interferometry. We can do it reliably. It's nice. So now we are asking question: can we learn something about the material? So for that, of course, we do theory. So we went back and started working on different kinds of theory. One kind of approach that we have taken is that, okay, we have an input state, we have some giant spectral amplitude, goes into the system, and then it comes out with my giant spectral amplitude modified by some second order scattering function. Now think of this: when my two photons go in, they generate excitations. The excitations don't talk with each other, they don't talk with anything. Okay, then it comes out, nothing happens. There is no interaction driven by my material. Okay, that's the boring one, where my second order scattering function is simply the product of first order scattering. It's like a linear response. You will get spectral filtering, nothing else, right? Like what you would expect to do absorption. But let's say there is some kind of interaction potential. If there is some kind of interaction potential, then I can expand out and write down my second order scattering. It's a very interesting method which has been put here in this paper, and we can now characterize and calculate how the modified joint spectral amplitude looks like. And we can characterize this by a parameter called entanglement entropy. Entanglement entropy is telling you how correlated my photons are, basically how good the JSA is. And what we see is that in the limit of slow fluctuations, we all know the limit of slow fluctuations. Interestingly, the entanglement entropy depends on the magnitude of bath fluctuations and also reaches a maximum. This sigma square is what we call as inhomogeneous broadening. We all know this, and it has a beautiful kind of line shape, kind of behavior. So basically, this initial measurement kind of calculation showed us entanglement entropy, which is characterizing the spectral correlations between my two photons, can indeed probe bath fluctuations. Now, this is random bath fluctuations. The interaction potential that we put out is some random bath fluctuation. But now we can go back and kind of explicitly include many body interactions, like exciton interaction, but not random bath fluctuations, slow fluctuations. If I do that, then you will see a dramatic change in the JSA. This is my input JSA. I put in a system. This is a Hamiltonian with some exchange and some interaction, Coulomb interaction here, and you see a dramatic change in my JSA, which is kind of fascinating, which kind of actually gave us enough motivation to go and explore methods to measure JSA. In fact, one of my collaborators jokes that I committed my life to measurement of JSA, and I'm risking my life almost to using this method. The idea is, again, going back, kind of is to say that if I launch my two photons, the only way the two photons are going to interact and change the JSA, which is beyond spectral filtering, is through a many-body interaction term. And so I should be able to extract this many-body interaction term, for example, bi-exciton interactions, without doing complicated, high-intensity nonlinear spectroscopies. Okay, so that's the kind of perspective that we are developing. So three emerging perspectives that I showed: Angumandal, quantum process tomography, and JSA. All these three giving some access to characterizing system bath interactions, either in the form of homogeneous line widths, bath fluctuations, or many body interactions in different forms. As I said, it is still emerging. A lot of scope, a lot of space to kind of grow. Okay. All right. I think we can end the course. Well, tomorrow is also part of the course, so we can end the course with this statement. Okay. Questions? How to choose a reference medium? One that matches with your light to begin with. Now we are doing different things. So, in my opinion, this is again an opinion. In my opinion, if I take intrinsically a weakly coupled system, it will work in a homogeneous, in the Angumandal kind of thing. I will not be having access to a many body interaction. Okay, so in my opinion, you need to have a strongly coupled microcavity in order to imprint the nonlinear interactions of the material onto the photons. Otherwise, it's too weak. Think of it. If it's too weak, my photons go only 1 in 1 million photons will see this interaction, which means when you actually do a measurement, it will not make a big difference. So if you go into strong coupling, then you're increasing the probability of putting that imprint of many body interaction on top of the photon. So in that sense, I want my resonant medium to be a polariton state, or a strongly coupling or ultra strong coupling cavity, coupled cavity. In the weakly coupled cavity, you can still measure the defacing rate, in my opinion, linear response functions. I think that is still an interesting avenue. But many body interactions like this, what I was telling you about, if you just put a medium there, you may not see it simply because it's too infrequent. That's the answer. Are you satisfied with the answer? Okay. Any other question? All right, let's close the course. Thank you.